Welcome, everyone. Today, we're diving into Freeman Dyson's captivating article, Birds and Frogs, from February 2009. In this piece, Dyson takes us on a journey through the rich history of mathematics, from Hilbert's problems to the Bourbaki group, revealing how the minds of great mathematicians work. He highlights the contrasting approaches that shape the world of math and science, offering unique perspectives that drive innovation and discovery. If you find value in this content, please support us by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No membership or account required. Now, without further ado, let's jump into this fascinating article. And this is definitely a fascinating article. And in the introduction, what he does in this first passage is tell us that he is a frog himself, and that mathematics is both a great art and an important science because it combines generality of concepts with the depth of structures. And I found this in the opening passage fascinating. Further, what he does in this passage is state that mathematics thrives on the combination of both birds, who see broad and unifying concepts, and frogs, who focus on detailed, specific problems. This diversity is essential for richness and the beauty of mathematics, hence the generality and the depth of structure. Okay, couple other great things in here that he relates with Einstein, which he says that this is for the Einstein Week lecture. And then he goes on to say here that Einstein, though primarily a physicist with mixed feelings about mathematics, exemplified a bird with his far-reaching vision, but relying on mathematicians for technical details. The collaboration between broad vision and detailed analysis is crucial in both mathematics and physics. And this segues us straight to a second section on Francis Bacon and René Descartes. And both of these were great philosophers in the 17th century, and they had two main objectives, or they formulated two types of science that they were trying to establish here. And, in the early 17th century, Bacon and Descartes introduced modern science with contrasting approaches. Bacon emphasized empirical data collection, so induction, while Descartes focused on logical reasoning or deduction. Now, with these two things being a very big primary focus of the paper, I think it's a good idea to see what we mean by induce and deduce. Okay, so induce is to lead to or bring about reasoning or influence. In the context of logic and reasoning, induction refers to the process of deriving general principles from specific observations of instances. It involves making broad generalizations based on a limited set of data. Can we actually compose everything of data humanly imaginable? Probably not. Deduce, however, is to derive as a conclusion from something known or assumed, i.e., to infer. In logical reasoning, deduction is the process of reasoning from general principles to specific instances. It involves applying a general rule to a particular case to reach the conclusion that logically follows. And setting the precedence of the paper with this, we can kind of see that the Baconian point of view is that of the frog, which is dealing in gathering the data, dealing in the very nitty-gritty of a very specific thing, which we could see highlighted in green. The likes of Faraday, Darwin, Rutherford, they all followed that line of reasoning, whereas Pascal, Laplace, and Poincaré were Cartesians. They liked having the deduction aspect of everything, so pretty cool in that aspect. That being said, he goes on to reference how, Bacon advocated for scientists to explore and gather facts to uncover natural laws, whereas Descartes believed in deducing laws through pure thought and logic. Both methods have driven scientific progress over the past 4 centuries, with English scientists often following the Baconian approach of imperialism, or not imperialism, of empiricism. Can't even say anything right today. And French scientists favoring Cartesian logic. Empiricism. There we go. Can't speak today. And to which he then quotes a kind of contrasting viewpoint with Newton as a Cartesian and later Marie Curie at the heart was a Baconian. And what he then highlights is how both of these figures exemplified the blending of these approaches and how one eviscerated the other perspective with their work as a whole. So pretty cool. And then key events in the 20th century, which he then gets into with the International Congress of Mathematicians in Paris, was the Hilbert problems and the Bourbaki group, which is the Bourbaki group was trying to unify textbooks and reflect on the ongoing interplay between empirical and logical methodologies. They were trying to unify things, whereas Hilbert's problem dug deep into very specific things. And that was kind of astounding to me how these two things were presented in what appeared to be opposite lights, but ultimately ended up having a nice interplay. And thus shaping the direction of the style of mathematical research. And that was pretty cool. I was not aware of the Bourbaki program, and he'll give us another later reference here for another one. But pretty cool to see Sir Bacon and Descartes. And then we move on to the third part of this paper, Jokes of Nature, which I found was, a little bit sidewinding, but then actually started talking about it was very awesome. And, the gist of this one was how the Bourbaki program aimed to make mathematics logical and systematic, but lacked the element of surprise found in historical mathematical discoveries, which often involved illogical jumps and improbable coincidences. Which is very weird to think, if you follow from one thing to another, that something would be a weird incidence and weird conclusion or illogical conclusion. But then he references things like Schrodinger's introduction of the square root of -1 in his wave equation, which is, why is complex numbers coming into something that's, quote, real, right? And stating that Schrodinger was a bird, Hamiltonian created something else earlier in classical mechanics, and then he sees that, well, the Schrodinger equation on its heart without I was just, it looked like a heat transfer equation, but then suddenly with I, it made sense. Suddenly the wave equation had something of value to the quantum world. And now it is the basis of all chemistry and most of physics. So nature works with complex numbers, not just with real numbers. And this gives me a segue to another podcast I saw with Carl Bender, a mathematical physicist. I can't remember what his actual work is in. But he talks with somebody, another student, I believe, about how complex numbers came about, their importance, and how they're complete insofar as the fact that they don't need any other number systems or structures like we need it for 0, negative, I. There's no other equation that needs another type of number system or schematic to have all the solutions. So that was pretty cool to me. And this also tells us or references back to a different article review about why complex numbers were needed in quantum mechanics anyways. So that was pretty darn cool. So nature's preference for complex numbers over real numbers was a surprising revelation, as previous mathematicians had just considered complex numbers an artificial construct. So that was pretty darn cool. And we see here that Abel, Riemann, Weierstrass, all them dealing with the complex variables as opposed to everything else. That was pretty cool. Another joke of nature is the precise linearity of quantum mechanics. Okay, this came out of surprise for pretty much everybody, and it's one of those facts that remains weird now. The precise linearity of quantum mechanics resurrected the study of Lie groups, or Lie groups, I see everybody pronouncing it differently, which became the central part of particle physics despite their initial obscurity and complexity. And one of the things he said here was, let's see. He says somewhere in here how, although the work by Lie was not used at the time because they were trying to apply it to classical theory, things like that, he said that this was math waiting to solve a problem, or solutions waiting for a problem. And that was an astounding thing to read coming through this. I'm just like, wow. Okay, so this was all well ahead of their timeline of what we thought. And this will tie back into something later when we get to string theory. Very cool. And thus, he goes on to a joke of, third joke here about how, quasi-crystals and the Riemann zeta function might have an overlap, and how the relationship between the zeros of the Riemann zeta function and quasi-crystals suggest a potential pathway to proving the Riemann hypothesis, a major unsolved problem in mathematics, which of course Clay Institute put out a nice $1 million prize for it, and the Millennium Problems, very cool there. And he says, well, look, if we take one perspective, which is the quasi-crystals, if we solve that, then we find that there's a connection with the Riemann zeta. We could do some stuff with the Riemann zeta. Of course, he tells us what a quasi-crystal is and all that other good stuff. But very, very cool to see how those things might potentially be together. And then he goes on to say how classification of one-dimensional quasi-crystals is challenging yet worthy goal that could illuminate connections across diverse areas of math and physics, a task suited for young mathematicians willing to tackle seemingly impossible problems. And it was really cool because he talks about both the Riemann hypothesis and the quasi-crystals, and talks about how weird things like the PV number was the coefficient such that all of the roots of absolute value less than 1. That's only one type, and if you reference Hilbert's questions, you'll see that he has a lot more than just the integer values that he wants to tackle. And so, yeah, this was a very nice overview of how two things could be back together. And I kind of like this last bit here of this section where he talks about how Baconian point of view, the history of mathematics is a history of horrendously difficult problems being solved by young people too ignorant to know that they were impossible. And there was another article about the blending of stupidity and science and how you need to have kind of this weird hapless hope and just keep chugging away at whatever problem you have. Very insightful concept there. And I believe there was another person who solved problems on the board because he missed class, and it was his thermodynamics professor, Boltwig, something like that. I can't remember the story off the top of my head. But he was late to class and just thought they were homework problems, so he ended up solving them because he was too ignorant to know that they weren't solvable. So I think the kind of anchoring that we put in our head on these problems can detriment us in some aspects. And then we get to section number 4 with Abram and Hermann Weyl. And Freeman Dyson discusses his experience with Abram at Cambridge, which of course was difficult due to World War II, highlighting their lifelong friendship and how Abram influenced his mathematical thinking as Abram was his advisor. And now Abram was famous for solving the 𝐀𝐤 problem, which involved finding the smallest area of a line segment that it can cover while rotating 360 degrees. He proved it can be less than, let's get the exact quote. Surprised everyone by proving that the area covered by a line, it turns out, is less than epsilon for any positive epsilon, not the pi/8 thought with the other one. And, this is a little bit over my head at this point, but that was very cool. And he talked about how this was more of a frog problem, very narrow in scope, but it had ramifications elsewhere in other aspects later. And then Abram gave it an elegant and deep solution, which revealed a connection with general theorems about the structure and sets of points on a plane. So although it's very narrow in scope now, it might have implications later. And then he talks about how the architectural approach of Abrams was. He builds out of a simple elements a delicate and complicated architectural structure, usually with the hierarchical plan, and then when the building is finished, the completed structure leads by simple arguments to an unexpected conclusion. Very cool. And now he contrasts this because Abram's work extended to dividing linearly measurable plane sets into regular and irregular components, a concept that Dyson attempted to expand to higher dimensions. Okay, and then of course we see how this leads us to Abram being a frog, focused on a very specific problem, in contrast with Hermann Weyl, who was a bird who sought grand connection in mathematics and physics. And of course, I think his work now is starting to be actually utilized to a much higher degree than even he thought possible at the time. Because Weyl's major contributions was the concept of gauge fields. This is what we've been talking about in the quantum mechanics problem sets that we've been working through. Very important for us in the higher levels to understand these. And initially in the classical physics and later integrated into quantum mechanics, this didn't come to fruition while Weyl was early attempting his things because he was trying to fit it to a classical world. And this all changed, and the whole change was to change from the real numbers into complex numbers, which brings me back to that podcast with Bender about how he, manipulates and the analytic continuation of the complex numbers. So very important for us. And because of that switch, that's what made it so applicable to quantum mechanics and field theories for QFT, things like that. And then we see here that we get again the electromagnetic potential and the laws of conservation of charge became a consequence of local phase invariance of the theory. So wow, this was done at a time and just blew my mind. And then of course a nice block about what Hermann Weyl was the one who made major contributions in the greatest number of different fields. So I'm sure someone can argue whether that's true or not, but it definitely seems very appropriate now, all the work that he did, considering what Hilbert and Poincare and everything else. I'm sure in 100 years he'll be talked about as one of the greats as well. Very cool stuff. And unfortunately, Weyl's, died not too long after all this was being put into work, so he wasn't able to see everything that was going to come out after he died, clearly. And to which Freeman actually wrote his obituary, praising his contributions across various fields and his aesthetic sense of choosing beauty over truth in his work. And here's the quote: "My work always tried to unite the true with the beautiful, but I had to choose one or the other. I usually chose the beautiful." And of course, you're kind of left in a nice headspace after that. However, it wasn't until 50 years after the golden age of experimental physics and observational cosmology and astronomy became in, and thus the Baconian point of view became much richer. Quarks and supersymmetry, multi-universe, all that stuff. Then, of course, following that, you had the period with P versus NP as far as computationability. So we could now use other methods that we couldn't have before for the Baconian perspective of data and induction. How cool is that? But, not to be astray, the next section talks about Frank Yang and Yuri Manin, which you probably know Manin from 3 Blue, 1 Brown, the Manin Library, and even the talks that Grant Sanderson has given referencing Yuri. And I think after going through this and seeing a little bit of the text myself about Yuri, I can definitely see why. And so despite the challenges, notable physicists like Frank Yang have made significant contributions because Yang took over Weyl's spot up there at Princeton, and such as the Yang-Mills theory of non-abelian gauge fields building on Weyl's work. So it's not like that spot was left in bad hands. Very cool there, and of course Yang-Mills is definitely something to dive into. You could spend a whole year on that and still not understand it. And then of course we see here, again referencing to the playlist of quantum mechanics, quantum mechanical spin, the generators of the simplest non-abelian Lie algebra, A2. So, again, all these things do tie together. It's just a lifelong journey of seeing how. Okay, and then we go on to see here that Yang's theory extended gauge fields to non-commutative Lie algebras, forming the basis of the standard model in particle physics, integrating Einstein's theory of gravitation, or therefore attempting. Of course, Christoffel needs to be used for Einstein's work, but very cool. And a nice quote here that was translated was, "The strongest argument for my theory seemed to be this, that gauge invariance was related to conservation of electric charge in the same way that coordinate invariance was related to conservation of energy and momentum." Okay, that was Weyl's final thoughts on everything before passing, and that is wild to think that he could have that insight, but I guess in hindsight, it all looks easy. In the middle of it, not so much. Okay? And then, of course, this leads to a concept that we're getting into now, how symmetry dictates interaction, and gauge invariance is eminently connected with the physical conservation laws. We're seeing that now in chapter 6. Okay? But shifting perspectives, now we get to Manin, and how Manin's book on the mathematics as metaphor highlights the importance of linking different mathematical concepts, suggesting future unifications between number theory and physics. As we can see here, all in the annotations, Manin did a lot of work that I was not well aware of, but this is definitely highlighting some nice things. And then, of course, Manin argues that mathematical progress comes from research programs, not merely solving problems, highlighting the influential programs like Bourbaki and Langlands as sources of innovative ideas, which you can see highlighted in blue. But some other nice little things that became relevant to what we see now, like coordinates, fluxions, i.e. calculus from Newton, symbolic logic, and Riemann surfaces, are all metaphors, extending the meanings of the words from familiar to unfamiliar context. Okay, so I think it was a really good gateway to include this. I definitely had no clue about this perspective at all from Manin, so I'm glad that Dyson put it in there, and I'm glad I read it. Very cool paper thus far. Makes me think what else we need to start investigating outside of just unifying. And so then we segue to John von Neumann, which of course was just a galactic giant of mathematics and physics in the time that he was working on it. And to the point which he developed the first satisfactory set of axioms for set theory, avoiding Cantor's paradox, which Kurt Gödel later used to prove the undecidability propositions, changing the view of mathematics to an archipelago of structures with diverse axioms, which you could see here in the green. And then Kurt doing his work, incompleteness of course, but that didn't stop Neumann. He kept going forward, and thus provided a firm mathematical foundation for quantum mechanics by creating the theory of rings of operators, akin to how Newton developed calculus for classical dynamics. And I thought that was cool. Couple interests of Neumann was his interest in bombs, hydrogen bombs, and meteorology using the computer. And he built a whole computer to prove this, which led to one of his other things that he didn't understand, which was chaos. And he says here that believed that computers could control weather by identifying and manipulating unstable atmospheric regions, but he was unaware of chaos theory, which later showed that small perturbations lead to unpredictable outcomes. And chaos is something I hold dear because I think it is simply fascinating. Of course, Neumann was wrong, and thus we get chaos theory thanks to Edward Lorenz, and I can't stop looking at that. Though interesting here enough, he goes on to say how it wasn't really, or Dyson tells us here that Edward really wasn't the first one to consider the chaotic effects, but that was actually Mary Cartwright, because she dealt with amplifiers with the van der Pol equation, and that was wild. I had no clue, but I'm glad that credit was reallocated to her in this particular paper. And of course, because of the perspective of Neumann being a frog, not a bird, when he was invited to give a talk at the Congress, he ended up letting everyone down, and his work on that lecture was left out. And they were not too happy about that, because they were expecting him to be kind of Hilbert and give the next set of problems. And this is where Freeman goes into, well, he could have just said, had he known about chaos theory, he could have talked about weak chaos. And the concept of weak chaos, where chaotic motion remain bounded and do not cause violent instability, is still an unsolved problem. An example is the solar system, where orbits are chaotic but stable enough to prevent system from flying apart over billions of years. So weak, chaotic because it remains bounded. Very cool. It seems as that chaos is almost universal in the world of classical dynamics, which of course there should always be, in my opinion, but we'll save that discussion for later. And thus, in weather systems, weak chaos results in unpredictable yet bounded temperature variations, essential for survival on Earth. Understanding why chaos remains weak despite no physical conservation laws enforcing this remains a significant challenge. And then it talks about how, between two locations, we're not going to get more extreme to one than the other, but we can range, in a dynamic, chaotic way. So very tight there. But this leads us to the next point about rigorous theorems being the best way to give the subject intellectual depth and precision. And until you can prove rigorous theorems, you do not fully understand the meaning of your concepts. And this is where he talks about the Lee-York theorem, which explains the prevalence of chaos, but not why often it is weak. So clearly further research is needed. So although we can have pretty pictures and stuff, that ain't going to cut it. You need the rigorous theorems. And this leads us straight to string theorist. And this was more of a cautionary passage here. And in hindsight, I do agree with the caution, because first they are, first-rate mathematics, which of course 𝐬𝐤 and Singer proved and loved. But also we need to be careful because string theory has significantly advanced mathematics, creating new methods to solve previously unsolvable problems. Okay, think about how Lie did that with the Lie algebras that were used 50 years later. And it is highly regarded by leading mathematicians despite being developed by physicists. So we got to be careful there. Nice mention here of Ed Witten and Juan, I don't even know, Malacina, something like that. I'm sorry if I mispronounced that. And he talks about, Dyson talks about the anxieties about string theory on a sociological level rather than scientific. And this is where he talks about how, although string theorists believe their work described the physical world, the theory remains untestable by experiment, existing separately from mainstream physics. Efforts to find testable predictions have been, thus far, unsuccessful. And the popularity of string theory we need to be careful of, because of the concept of both intellectual appeal and economic factors, mainly economic, leading to potential job risk if the field becomes unfashionable. And then here Freeman speculates that string theory might find its place in the future, similar to how Lie groups became central to quantum mechanics, but acknowledges that this prediction may be wrong. And I think that's fair, especially because it's cheaper to put a theorist in a desk than it is to build a collider, things like that. So be aware if you like it, but, better to have all cards on the table and make a decision than not. Here's that quote I was looking for. They were a solution looking for a problem, in reference to the Lie groups. That I found holistically wonderful, and that could definitely disparage somebody if you find something cool but don't have wherewithal to actually see it through. And then in this final passage, he talks about Manin again and kind of a psychology approach. And in the book of Mathematics as Metaphor, Manin explores diverse subjects beyond math, such as the collective unconscious, human language, autism, and methodology, reflecting the rich intellectual traditions of Russian and intelligentsia. I'm so bad today. And then, of course, this tells us about Carl Jung's theory of archetypes and delves into how these shared mental images and intense emotions reflect our collective memories of joy and suffering, using the example of the dead city archetype to illustrate the concept. Thus, the recurring theme of the dead city in various art forms symbolizes human destruction and collective unconscious forces, Manin argues for the necessity of creating a collective conscious based on the hope and reason to counter these destructive tendencies. And that is a great way to end this, because I hope that this at least elucidates a picture of how people start to present concepts. Are they from a big point of view or very, very narrow? Some way or another, we have to find the connections to all of them. You can't build a large structure without a good foundation. You can't see the frogs if you're flying above in the rainforest canopy, but both are definitely necessary, and I believe Dyson Freeman does a great job of exploring this concept. And of course, this will be one of many articles that we dive into, but this one I just had to, because it talked about a lot of things we're seeing now in quantum mechanics with the we're dealing with very specific problems, but they are the foundational building blocks for something much larger. So until next time, stay curious.